Okay, we're going to review continuity. First of all, a polynomial is continuous everywhere. There is no points of discontinuity on a polynomial. On a rational function, you can have two types of discontinuity. You could have a whole, or you could have a vertical asymptote. So when your denominator is 0, that's where you have your points of discontinuity. A rational function is continuous at every point where the denominator is non-zero. It has discontinuities at the points where the denominator is equal to 0. So if you recall, if there's a common factor in the numerator and the denominator, and those factors cancel out, whatever factor canceled out, whatever makes that equal to 0 is a whole. However, if the factor in the denominator doesn't cancel with something in the numerator, whatever makes that equal to 0 is your vertical asymptotes. So those are points of discontinuity. So let's talk about point continuity. It says f of x is continuous at x equals c, some x value, provided that all three of the following are true. The first thing is the function has to be defined. So a whole, the function is not defined. A vertical asymptote, the function is not defined. Then the limit would also have to exist. Where the function is defined has to be the same as the limit. So it is possible for you to have a function that is defined at a certain c value, and the limit exists, but the two do not agree. And here is one example. Call that c. So is the function defined at c? Yes, it's right here. Does the limit exist at c, coming in from the left and the right? Yeah. However, is the function defined at the same y value as the limit? You can see that these are two different y values. So this function right here is not continuous at c. So you have to make sure, this is the important step that you need to check. These are the three things that have to be stated in a free response in order to prove point continuity. Then there's removable discontinuity, which we've already talked about. A function f is said to have removable discontinuity at x equals c, provided that the limit exists at x equals c, and f is continuous at x equals c. So either because, f is not continuous at x equals c. So the reason would be f is not defined, or the function does not equal the limit, which is the case up here. The function does equal the limit. Down here, the function does not equal the limit. So here is the case of removable discontinuity. Then we have interval discontinuity. And here's what interval continuity says. I don't know if I just said discontinuity, but interval continuity. It says a function is continuous on the closed interval. So that means from a to b, including a and b, if it's continuous on the open interval. There's a little typo there. If it's continuous on the open interval, then it's also continuous on the closed interval. And that's just something that you're going to have to accept for interval continuity. And we talk about, later on, we talk about increasing and decreasing over an interval. So if it's continuous coming from the right and it's continuous coming from the left, then it's going to be continuous in the closed interval. Okay, that interval discontinuity, or interval continuity, I should say, is not that big of a deal. Now, IVT, or the intermediate value theorem, Basically, what the intermediate value theorem says is if you're on a closed interval and you have any number, some y value in that interval at A and some y value at that interval in B, that if there's a sign change, then there's at least one solution of the equation, f of x equals 0. And all we're saying is that if there was a sign change in that interval from f of A to f of B, then it must have crossed the x-axis. That's the intermediate value theorem. Okay? Same thing with the first one. If your y value, say in the interval, as long as it's continuous, as long as the function is continuous, if there's a y value, say of 9 at A, and there is a y value of 6, and the function is continuous, then there is at least one value in between those numbers on the graph in between that interval. Now, I don't know if that made sense to you, but let's go ahead and read it again. If f is continuous on a closed interval, A to B, k is any number between these two y values, so to speak. Okay, it's inclusive. So if this is 9 and this is 6, then k has to be somewhere between 9 and 6. Okay, so there's at least one number, x, such that f of x is equal to k. There's some x value in the interval from A to B whose y value would fall in between 9 and 6. It's kind of common sense. Don't overthink it. We call this IVT, and it does come up quite a bit, so you do need to know that. Okay, some other properties for continuity. If f and g are continuous at some point, then their sum or difference is continuous, their product is continuous, and their quotient is continuous, as long as your denominator does not equal 0 at those values. And then we have the composite functions. We'll discuss those later on this year, but if you are taking the limit of a composite function, you can take the limit of the inside function and then evaluate your answer at the outside function. So again, the limit of a composite function is evaluating the limit of the inner function, and whatever your answer is, you evaluate that on the outer function. That's composite. Okay, the squeeze theorem. We're going to watch a video on the squeeze theorem. It is in the AP classroom. That's the first video on topic 1.8, and that will explain this a little bit more thoroughly. The squeeze theorem isn't that big of a deal. And then last but not least, some trig limits to memorize. All of these can be proved. They are proved in the textbook through a process. The good news is you don't have to show me the work. You don't have to prove it. You just get to memorize it. Okay, so all of these are true. This b value, if this is the same and this is the same, so if that's a 3 and that's a 3, your limit is still equal to 1. 1 minus cosine x over x is equal to 0. So those may become useful to you when we're simplifying limits. So let's just take a look at this example right here. This does not equate to this because they're not the same. However, what I can say is that I can rewrite this as the limit as x approaches 0, and I don't want it to be a 4x. I would prefer it to be a 5x. Now I can't just change that problem, but I could rewrite the original equation like this. Here is my original expression, I should say. Here's my original sine of 5x over 4x. And all I did was multiply the top and the bottom by 5x over 5x. So I just multiplied this fraction by another fraction equivalent to 1. So I didn't change the value, I just changed the looks. Now, why is that helpful to me? Because I can rewrite it Now again, I don't have to separate the product. We learned that the limit of a product is the product of the limits. So we can do that, but we don't have to do that. But this right here, this goes along with this one right here. So because these are the same b value here, the limit of this is equal to 1. And the limit of this, the limit of a constant is a constant. So our final answer is 5 over 4. And there you